Let me actually start real quickly with telling you that the feedback, just those quick feedback questions you've given at the end of the problem sets, have been really, really useful for me to see, to get a sense of what you guys are thinking, what you guys are feeling. So please keep it up. There were a couple things that came across in the last feedback. So just to bring them up, a few people sort of commented that some of the math was feeling a little abstract. We wanted more examples, sort of connecting back to real systems, and that happened. You guys obviously typed that in right before Scott gave a talk about Atlas and LQR. So hopefully, that one was connected. Another question. There were also some questions about the HJB derivation, and luckily we had set up Michael to give some clarity on the HJB derivation. So hopefully those two were addressed. But if you have more questions or comments like that, then let us know. Another one that came up that I hadn't been planning to talk about in lecture, but a few people were asking about what the heck is Drake, and could you give us just a few minutes just to tell us what it is and this thing I'm downloading. So I won't spend much time on it, but let me just quickly say a few words about that. So first of all, you should know that the code that you've downloaded is actually the same code that we run on Atlas. So that's kind of cool. And in fact, you've downloaded most of the control code that we field in the DARPA challenge. We haven't put all the interface and all the perception and all the other things in there, but we made a decision as a team that even though the competition's coming up still, we've been working really hard on the code. We might as well give it away and maybe have more impact that way. And certainly it's a cool tool for class. So first of all, you've downloaded the code for Atlas. There's simulations, there's examples for Atlas. If you're doing the precompiled distributions, I don't know if you've watched the distributions accumulate. I've been trying to build more and more of it on Windows, honestly. That's the big, you wouldn't believe how many hours I spend compiling. If you came in my office right now, you'll see, some books and academic and pencils and papers, and then you see a build farm on the corner with a Windows machine. Now there's a Windows 32-bit machine, there's a Windows 64-bit machine, there's a Mac, there's a Linux, and every different permutation of MATLAB license and everything. So I'm working really hard to try to make it work on all your machines, just so you know. But the precompiled distributions are going to come basically with more and more functionality as they work on all the different machines. So the version you downloaded precompiled last week won't run all the Atlas demos. Atlas will just fall through the ground. But the one you'll download next week will be able to run all those demos. Okay, if you want a quick high-level view of what Drake is, you can always look at, if you just go to the Drake website. The documentation is sort of always a work in progress, I guess, but it's compared to anything else I've ever written, it's actually fairly good. But so you can go to this Doxygen page and you can search for any of the methods and everything like this. But the thing you might not have realized when you're working with it and running a few examples is that it's really built to try to be. It's built in object-oriented MATLAB to try to be a way to provide some clarity to all of the structure that we have in dynamical systems. So it's all about nonlinear dynamical systems, and it's about exposing the structure in those systems so you can write algorithms that take advantage of those structures. So that's a theme in the class, and that's a theme in all of our work. And so, for instance, there's this big class hierarchy that everything's a dynamical system, and then you'll see polynomial systems are, our affine systems are polynomial systems, are Drake systems, linear systems are examples like this. So there's this whole sort of class hierarchy of different systems, right? Linear is affine, is polynomial, is Drake. And there's some algorithms that we know how to write that we really know a lot of what to do with linear systems, and we know a little less about affine systems. There's some tools that work for polynomial systems that are very powerful. We're going to get into them in the next few days. And so basically by writing dynamical systems in this language, where you define basically the dynamics, the update, the output, and making sure that you expose the structure, then we've populated, you'll see in the polynomial system class, for instance, lots of different algorithms. Well, first there's sort of the standard thing that defines the class, And then there's lots of different algorithms that are built on top of that structure. The most important one in the polynomial systems is we know how to estimate regions of attraction for polynomial systems. And you're gonna learn about that next week. And if you look in different parts of the class hierarchy, you'll see, for instance, the manipulator systems. That's what we've been talking about now. So the manipulator, any manipulator is something that has this form, H plus C plus equals BU, right? And for those systems, we know lots of things. We know that it's control affine, and these are the algorithms implemented at the manipulator level are the ones that take advantage of that structure. Okay, so what you've downloaded is a big software package that tries to be clear about its thinking in dynamical systems and has lots of algorithms implemented for each level of those dynamical systems that we'll be exploring through the course of the class, and there's many that we've implemented in here that we won't get to in class. So you should feel free to poke around and play with it. Also, it's open source. You should feel free to contribute, and if you're excited about it, then more and more people are using it. There's a chance it'll actually get bundled with MATLAB's robotics toolbox coming up. We're talking to MathWorks about that. So if you had an example that you like, or if you even have a final project you do for this class and you want to push it back into Drake, I'd be thrilled to do that. And we'll see how much use it gets in the long run. But for now, it's a tool that hopefully will get you to be able to run the algorithms we're talking about in class very efficiently on your own machine. You guys have experienced a little bit of startup cost and are running things like value iteration and stuff so far. But that's actually something we've never been able to do in class before, just distribute reliable code that lets you just run those examples. I mean, that's took a lot of work. Okay, so maybe that gives you a sense of what Drake is. I mean, the biggest thing is that I think that's exciting about it is it really, it's not just for running toy examples for the class. We actually use it to run the robot. We run MATLAB on the Atlas computer while Atlas is running. A lot of people think that's crazy. I acknowledge that it's borderline crazy, but it's allowed us to do very fast implementations of some of these complex ideas. And we really run Drake at 350 hertz on the robot when he's moving around. And the stuff that Scott showed you is real. It's actually running the same code you've got on your hard drive. Cool. Okay, so that addresses some of the feedback, and it was incredibly valuable. And I hope you liked the lectures by Scott and Michael on Tuesday. I put in some questions, for some of the feedback questions for this time. If you have some positive things to say about those what Scott or Michael did, or negative things, I guess it's possible. But let us know. I mean, that's for me. That's great. I mean, if you use a lot of superlatives about how great Scott is, and Scott's applying for a job to be a faculty next, then I'll use your words in his letter, and he'll get a job. So be nice and tell us how great he is. Okay. So the goal for today is to think about to continue thinking about the Acrobat and the Carpool and the sort of model underactuated systems that are simple in the sense that there are a few degrees of freedom, so we get to think deeply about them. They're also they're simple in the sense that they don't have some of the complexity that we're going to see when we see, for instance, walking systems. You're not going to see impacts. You're not going to see hard discontinuities. The dynamics are basically smooth, with the only exception being the input saturations we've talked about a little bit. So they represent an important class of systems that we've been able to think about clearly. Last time we talked about, make sure, yeah, okay. Last time I was here, we talked about starting to apply the ideas of dynamic programming to the Acrobat and Carpool. And we said you could discretize the whole space and do the discretized value iteration that we know is going to work and we can rely on. There's no worries about whether it converges or not. It's guaranteed to work. but we would have to sacrifice either a lot of computation time or a pretty sparse discretization of the space. We did a little better, I think, using the linearized dynamics. Around some operating points. So for balancing the carpool or the acrobator on the top, we were able to come up with pretty good approximations. If you remember, I tried to argue that the pendulum dynamics, which looks, in this characteristic form, very, very nonlinear, in a sense that we were actually getting a pretty good approximation of it with our linear approximation, which captured the nonlinear dynamics in some vicinity, right? We got this linear phase portrait that captured sort of the basic dynamics of the pendulum, in this case, of the undamped pendulum. And it was actually a very good approximation here, right, of all the sort of things that happen. But of course, if you start using that for the whole space, it becomes an increasingly bad approximation. And maybe like if you look at the point where it's telling me here at the position I know is a fixed point, it should have a zero vector field right there, right? The linearization about the top would tell me that I've got a huge vector, at the origin. So it's sort of there, it's really bad, right? And it's just going to get worse going this way. So it was sort of good as a local approximation of the dynamics, roughly there. So, and one of the things we're going to do, for instance, that region of attraction code that I just alluded to, one of the things we're going to do soon is be able to calculate that more precisely. And you learned about what the definition of a region of attraction was, but you could ask the question, if I design a linear controller for my nonlinear system, for what initial conditions does it return? Is the closed loop system going to be stable to this fixed point, right? You could ask for the region of attraction of this fixed point under the closed loop system, and that would tell me when the linear controller is doing the right thing. And we're going to talk about that in detail next time, okay? But you have a sense, there's some algorithms that actually tell us where that linearization is going to work and where it's not going to work. But we really haven't captured with our optimal control tools yet all the richness of the nonlinear systems, not in a smooth, continuous, beautiful way, okay? So not everybody does optimization here. In fact, that's a relatively newer trend to be able to formulate all these things in the language of optimization and reliably solve them. There's a long history of people thinking about the nonlinear dynamics of things like pendula and carpools and acrobats, more in a more sort of physical way, right? So there's a branch of nonlinear control for underactuated systems in particular, where they really use physical insights and write down simple nonlinear control, relatively simple nonlinear controllers that are based on understanding the system that can solve these problems in the nonlinear sense. So before, I'm going to, in the long run, I'm going to try to convince you that optimization is a good way to go the whole way. But to make sure we appreciate the optimization and put it in context and understand the physics of the system, I want to spend today talking about sort of the nonlinear approaches, the non-optimization nonlinear approaches to controlling the acrobats and carpool. Okay, so. In particular, the thing we didn't solve, we sort of separated the problems before into swinging up the acrobats and cartpools and then balancing. So we sort of did the balancing, but we haven't done the swing up task. And so today we're going to do nonlinear control for the swing up. And it's really, I think it represents sort of the not optimization based, the more traditional approaches to nonlinear control. And I like it. They're going to be specific examples that work specifically for these systems. But the style, the feel of how we get them is really, I think, very representative of what you'd see if you applied it to different systems. Okay? All right, so we're going to do it for the pendulum first, where we can really understand everything, and then we're going to see how it applies to the more complicated systems. Okay? So let's start by doing swing up for the pendulum. Okay? Okay, I think I can tell you very, very efficiently what the big idea here is. Okay, so we take the orbits of the pendulum here. This is theta and theta dot. Okay, and I just drew it a minute ago, but we're gonna think about this. There's lots of orbits of the pendulum. The undamped pendulum, in particular, has this eyeball-looking orbit. Okay. Now, and it has, of course, other orbits here, but this particular orbit of the undamped pendulum has a name. Okay, it's a special orbit because it visits a fixed point. Okay, and it gets a name. And now, if you think of it as there's some argument about this, but I'm going to call it the homoclinic orbit. Okay. If you think of these as two separate fixed points, you might call it a heteroclinic orbit, but that's the same fixed point. That's just rotated around by 2 pi, right? So I think it's good. It's right to call it a homoclinic orbit. Okay, the homoclinic orbit is the orbit which visits the unstable fixed point. Okay, it's deserving of a special name. Okay, if I start on this orbit, I will find myself at the upright. Okay. So the basic idea that we're going to try to pursue with our nonlinear control here is if I start myself anywhere in the system, I could try to drive directly to the fixed point, but that's maybe hard. It's a little easier, it turns out, since I have limited control authority, to say wherever I am, I'm going to just try to drive myself closer to this homoclinic orbit. Okay? And then if I can get to the homoclinic orbit, and if I can stabilize the homoclinic orbit, then I can just ride it in and get myself to the fixed point. Okay? So that's the idea. Let's try to stabilize the homoclinic orbit. Okay? So we're going to come up with a nonlinear controller that stabilizes that orbit and then let it ride the wave right to the goal. Okay? So how do we, if I had to write an equation down for that orbit, how would I write that down? Well, how is that orbit defined? What's the natural description of that orbit? Say it again? Well, it's actually not a circle. It's maybe if you put it in the right coordinates, you could say maybe, but in my theta versus theta dot, it's not a circle. Yeah.
The energy is constant.
Right.
And it's going to be the energy the same as the energy at the top.
Exactly. Right. So this is a constant energy orbit. This is an orbit of the undamped pendulum. Exactly. And in fact, the way I had defined energy, it's going to be where the total energy equals mgl. Okay? Right. We'll write it down. But it's a constant energy. Okay, so a basic idea would be if I'm not at the right energy, if my energy is less than mgl, I'll try to push energy into the system. If my energy is greater than mgl, I should take energy out of the system. And maybe that'll sort of stabilize the homoclinic orbit. Drive myself to some known energy level. Okay, so let's think about how we're going to do that, right? So the big idea is going to say drive my energy of the system to this, let's see, to my energy desired. Okay, that's our big idea. So I'm going to transition, so I'll give a pause. Okay, so the energy of the system. Well, let's just. I'm going to need it in a second, so we'll just remember that the ml squared theta dot plus mgl sine theta was 0. This was our original dynamics, but we'll do it like this, right? That was my equations for the pendulum. And my energy is what? 1/2 ml squared theta dot squared. That's my kinetic energy. And then minus mgl cos theta, because I define 0 to be at horizontal. So what I want to think about now is how do I regulate that energy? Okay. Now for pendula, for 1 degree of freedom systems, you probably, if you're mechanical, if you're a mechanical engineer, for instance, you'll know the answer. But I want to show you a slightly more procedural way that will make sure we get it from the equations of motion. Okay. So what I care about here is how this energy is going to change over time with respect to my control input. Okay. So let's think about what's the time derivative of this energy. Okay. So I'll just differentiate this, right? So I'm going to get 2 cancels that out. I get ml squared theta dot plus theta double dot, and then plus mgl theta dot sine theta. Okay, so another good piece of feedback was that the dots are sometimes hard to see. Let me see if I can make them really big. See, this is your comments in action. That's a big dot. That's 2 big dots, and that's 1 big dot. All right. Okay, now the cool thing is we can substitute in here. We know what theta double dot is in terms of u. So we're just going to do some manipulation here. We're going to drop our dynamics into this equation. In fact, I know that ml squared theta double dot equals this, right? So I'm going to go ahead and write this down as theta dot. I'm going to substitute ml squared theta double dot for this here. That's minus mgl sine theta. Right, that's this ml squared theta double dot became this. And then plus, and I'll write it in the same way just to and that conveniently simplifies very nicely to just being u theta dot. Okay? So we just got that from the algebra, and we'll get that from the algebra for different systems that aren't as mechanically simple. We'll get something slightly more complicated here. But if you are a mechanical engineer, you'll say, duh, I already knew that. That's just power. That's torque times velocity. Right? Right? So that's a good sanity check. Our algebra gave us something mechanically sensible. Okay, so now we have to think about how are we going to drive the system. We know how to change now. We know how to force a change in the energy given some input u. Okay, how do we come up with a nonlinear controller that's going to regulate energy? Okay, and it's really some very simple idea. We want to take E to some E desired. So I'm just going to write a simple feedback controller that drives E towards here. So let me define my error, my current error, just so it's in a nice simple coordinate. I'll say E tilde is E minus E desired. Right, so that's my error. And so E tilde dot, the time derivative of that is, since this is a constant, is just E dot. Is just U theta dot. So I'm going to now, this is where you start thinking like a nonlinear control guy, okay? Let's choose a nonlinear controller, negative K theta dot, times my error. Okay, that's my feedback controller of choice. Okay, because if I put this back in, that's going to imply the following error dynamics. It's just algebra, right? And then what does that look like? That's a nonlinear dynamical system. It's just, but it's a really simple one. I know if I choose K to be greater than 0, which I should do, right? Theta dot squared is always going to be greater than 0 or 0, right? So this thing, I can think of, I can reason about the dynamics. I can be sure that as long as theta dot doesn't stay at 0, if this is 0, then I'm doing nothing, and that's not so interesting. Okay, but as long as theta dot is positive or negative, or if it's non-zero, then this is some positive number times negative E tilde. So that's going to imply some sort of linear-ish, exponential convergence to 0, right? You should think of this as x dot equals negative alpha x. Oops, what happened there? Right? I'm going to have some stable linear system. And if E tilde goes to 0, that implies that E goes to E desired. Okay? As long as I don't stay with theta dot equals 0, right? And we'll write that more carefully soon, but let's just get the idea across, right? So, okay, if I start here in the downward configuration, then I'm going to stay there, right? Because theta dot equals 0, I'm never going to get out of it. But as long as any other initial condition, I'll have some theta dot. Even if theta dot goes to 0 temporarily, it's going to come back out, and so theta dot won't stay 0. I'll regulate my system, okay? And I'll have some control that will drive my energy towards energy desired. Okay, so conceptually we can see that even more, right? So if I think about this controller here, right? You could say when E tilde is positive, which is when my energy is greater than my desired energy, right? Then this thing is going to look like you're going to have a positive number times this. So you're going to basically remove energy. In fact, you look like a damper. Right? And when the energy is smaller than the desired energy, I'm going to add energy. Okay, very simple controller. But it captures a few things that happened here that are sort of in the nonlinear way of thinking. So we actually chose a nonlinear feedback here, which is my energy, which is a function of, it's a function of theta dot squared, cosine theta. It's a nonlinear term here. And I'm multiplying it again by theta dot, so this is a nonlinear controller for sure, okay? But it gives me a very simple behavior. All right, so what do we think this is going to do in the portrait, right? So if I have my pendulum, my homoclinic orbit, we're going to hope that if I'm here, and I would have normally just gone around like this, that this is going to drive my energy up, and I'll end up with something that goes like this, right? And eventually comes to the homoclinic orbit, and then rides the wave. It'll stabilize the homoclinic orbit, right? And similarly, if I start it outside, it'll take energy out, find its way to the homoclinic orbit, and go to the origin. Okay, so here's a question for you. If I stabilize the homoclinic orbit, have I stabilized at the fixed point? Is this a sufficient controller to make me not only get to the homoclinic orbit, but once I get there, am I going to stay there? I see some yeses, I see some nos. Why yes?
Well, we can try to drive the system to the origin. And if we can do that, we can just use coordinate transformation to go to the other fixed point. And we can set the desired energy level as 0. Then our controller will drive the system from any initial configuration to the origin.
Yep.
And if we achieve that, it means we can just play the orbit and we can drive the system to other.
I hear you. Okay, so certainly if we were to do the energy shaping where the desired energy was 0, we'd get something here that would do exactly the right thing and would stabilize the origin. If we did sort of change coordinates there, then you'd like to get something like this. But if we have saturations or something like that, that would get back us to closer to the feedback linearization idea. And we didn't actually need feedback linearization to write this controller, right? So if we just look at this controller stabilizing now this non-zero energy, then it's a little different than a coordinate transform from here to here. It's a potentially gentler controller that could get us there, right? I could just be pushing a little bit of energy in all the time and slowly get myself up without ever overriding it. So it might be a little better. Why no? Why do you? Sure.
So basically, at this orbit, you have unstable equilibrium. So you would need to have 0 speed to stop that. Otherwise, it's just gonna keep going.
Right. So will you have 0 speed when you get there? Yes, you'll have 0 speed when you get there. So that's actually okay. But if you get any minor perturbation here that'll knock you off, then you're not going to come back to here. It's not going to be, the point is not stable, right? Yeah.
Yeah, so our controller is only made to control the energy of the system, not its position. But the whole reason we selected this controller is because the entire homoclinic orbit has the same energy. So you will stay, if the controller is good, you'll stay on the homoclinic orbit, but you have no guarantee as to where. So once you get near the fixed point, you need to switch to that linearized controller to stay there.
Exactly right. So when you get here, if someone were to perturb me here, I will still stabilize the homoclinic orbit, but I'll go all the way around and then come back and visit again. But the second part is exactly right too. So once we get close, we already know controllers that'll work. So the idea would be to switch to the LQR controller when we get close enough, right? And defining what close enough is potentially hard. On the pendulum, it's easy. We can just pick a sort of threshold, and that'll be good. But if we can, that's where the region of attraction computation is going to come in later, okay? But let's just say right now, if we get close enough, we'll flip the LQR controller on and stabilize the orbit like that. All right, so this works. Okay, so another comment was, don't just show me the demos, talk me through them a little bit. Okay, so so really I wrote down exactly what we just said here. What I've done here, so in the software, a controller is just another dynamical system, right? So I made a new dynamical system. It's called my pendulum energy shaping system. We do a little bit of work here to make sure that they know that they're in the same coordinate frame, okay? But basically I just define this to be a simple system which takes its current input, comes up with an output. It takes the state of the pendulum as the input. It computes the energy using the equation for energy there. It compares it to the desired energy here, right? And then it does exactly our controller, okay? This is I'm jumping ahead a little bit, but if we had damping in the system, it can take care of that damping too, okay? And then there's a slightly more complicated thing that happens here to if you want to put that together with the LQR controller, then you actually end up with a hybrid system that's an event system, okay? But we'll talk about that later. I don't want you to get lost in that detail. But basically, we end up with a system that combines the LQR controller with the pendulum energy shaping controller, okay? And we make that into one. The controller is now a system that knows how to flip between those based on the region of attraction computation. Okay, and the way I'm going to now run this is I just make a pendulum plant. I turn the input limits off for the region of attraction estimate, and then I put them back on. And then I just take, my plant is PD. I've got my controller, it's C. I'm just going to say they're feedback combined. So take the output of that, put it as the input to this, the output of this, put it as the input to that, and then I'm going to simulate it. I'll simulate it 5 times from random initial conditions, okay? Takes a second the first time because it computes the region of attraction, which is dominated by loading the code that computes the region of attraction. But it's been simulating behind the scenes and I just didn't realize it. Okay, so it pumps up and it stabilizes just the way we'd think, right? If I have less aggressive input limits, then it'll just go almost straight up. But if I put strong input limits, then it'll do like you just saw. It'll pump up a little bit of energy every time, right? And then when it gets close, it'll turn on the LQR and right to the top. In more than 6 seconds. I guess I was like, oh, it's the torque limits are too high. I'll turn them down. But I guess I should have also turned up the simulation duration. All right. Okay, so that works. That's a simple nonlinear controller. Stabilizes the homoclinic orbit. Yep?
How much more efficient is it to like switch between the LQR and the energy controller instead of say like having some proportionality? Like I'm this far away from it, I want to multiply it, but this controller is input by this much, and this controller is input by this much. So that when you get close, you're having a bigger scale than that.
Right, so you want some soft mixing of the two controllers. Yeah, I think that would work fine as long as you have the property that you're doing only LQR when you get to the top, and you're doing something away. I mean, the problem is your LQR gains might do really big things. It might actually be hard to mix those in a soft, good way, right? Your LQR gains might be asking for a lot of torque, let's say over by the origin, and your energy controller is actually trying to give just a little bit of torque. So it might actually be non-trivial to mix those in a good way, right? Yeah, I think that would be the #1 problem, especially if you've, the LQR controller is not necessarily good at thinking about all the wrapping issues. The nonlinear controller, just by having the the sine and cosines inside the equations, actually handles all the wrapping of the coordinates very nicely. So I think that's probably the number one reason. But you're right, the complexity of switching is this extra logic of being a switched system that we'll talk more about later. And that's a pain. Yeah?
If we don't know the parameter of the plant exactly, how is this going to happen?
So that's actually one of the strongest sort of motivations for this, is that the controller, we could look at the robustness, okay? So all right, so let's say we had some errors in our parameters over here, okay? So let's say my estimated m wasn't quite my m, right? So what's that going to do? When I get my energy dot, I'm going to get some extra small terms over here due to that error, okay? So as long as I'm putting in an energy that overcomes those small errors, as long as E dot and E tilde dot is still less than 0, then I'm fine. And in fact, that margin is actually easy to make quite big, right? So if you think about it, the controller I'm doing is just applying damping if my proposed energy isn't quite right? So it's easy to apply damping even if I don't know the system exactly. I'm just taking out energy, right? Or I'm applying energy. So this is actually one of the good things about the controller, is that it's actually it's relatively insensitive to the parameters. Now, if I estimated my total energy of the pendulum wrong, then I might stabilize an orbit which isn't quite the homoclinic orbit, but it'll still take me close to the fixed point. And if I flip on the LQR and rely on some of the stability, the robustness properties of the LQR, which is known, then it'll still stabilize the fixed point. So this is a strength of the approach. Yeah.
Do you just switch the inputs? Like, is there just discontinuity when you get?
That's the simplest answer is yes, right? So if you've run some of your controllers and you see something about successive zero crossings in any of the examples, that's the switching. I'm actually simulating it accurately and doing an event detection of the transitions, and it does get a little gross, but in practice you could smooth it out and be fine. But the simple answer is yes, just a hard switch. Yeah.
So here you chose the U to be negative k theta dot.
I did.
You chose U to
Theta dot E tilde. Yeah.
You chose to be not dependent on the magnitude theta, but just the sign set. So you did negative k sign theta. So this is good because it says that if we put a little extra bump in the ends of the pendulum, then that'll be the most efficient way to input the torque. But if we just made it the sign of theta dot, then it would mean that actually if we put in the same amount of U at the bottom, it's actually going to do more than it would do at the end.
Yeah, so if you replace this with sine theta dot, you'd still get something that's always positive here. That would work.
Sure.
And I think the only possible motivation for this is really is speaking towards the smoothness of your control, right? Is that you have a nice smooth control function as a function of space until you flip once to your LQR, as opposed to a sine which might have which it's going to go to 0 and potentially flip, right?
Well, I mean,
Yeah, no, but I think that's a totally reasonable suggestion, and it'd be easy for you to try in the code. Okay, so so if you do have damping back in the equations, then this is again very easy, right? So if I did have my I'll just cartoon this because we already saw it worked, because I showed you the simulation too early. It's big dots, right? If I do my E tilde derivation, right, my same definition here, what I'm going to end up with is that my change in energy is U theta dot, as you'd expect, but minus B theta dot squared, right? So I'm going to lose energy based on my damping, right? Which is the same as, it's got to be that, right? It's just the same as if I commanded a torque which also had this damping torque, right? And so you can choose U to be plus B theta dot minus K theta dot E tilde. So that's exactly what you'd get from following exactly the same recipe, just saying I want to make my E tilde dynamics to be negative k theta dot E tilde. Okay, and if you want to make this dynamics true, even though you had some damping in the original system, then what it tells you to do, that same recipe, is run the same controller I did with the undamped system, but also actively cancel out the damping in the system. So apply some torque that counters the damping torque in the system. Yeah?
You use the damping torque. If it's in the right direction, it seems like you could also make use of it.
It's true. It's true.
Another thing.
Which this would sort of do, right? So it would, this would fight that and
you'd be a little bit better on the sub.
That's right. Exactly right.
Maintain like a continuous positive negative damping. Keep taking into account that. So if you're at K minus, you're actually damping, right?
It's true. It's true. Yeah. I think this would actually use less energy when the damping is doing the right thing. But you could imagine other cleverness that gets this to be some positive scalar times that always. Exactly.
So with respect to underactuation, one potential advantage of putting theta in the controller might seem to be that you've got a torque speed curve for your motor. So you might be able to put out more torque at higher speeds anyway.
Yep. Yep.
In terms of physical
that's true.
Behind that, I'm wondering if that's a part of choosing that controller.
Sure. Sure, it might be. I mean, in practice, this works well. I mean, so it's going to work well for more complicated systems too. Right. And there's little things like that might actually make a practical difference in why it works well. Yeah, I believe that. Okay, so let's see if we can extend this. I think the story for the pendulum is easy, but I wanted to just see the recipe of thinking about the error dynamic, the energy dynamics, right? And then writing a nonlinear controller. The insight here is that if I choose something goofy here, a nonlinear controller, I can make myself have a simple, nonlinear, but simple error dynamics and talk about the stability of the nonlinear system, right? And that's a trick that we're going to play again and again in the nonlinear control world, okay? So let's see it play out on the carpool, okay? So the equations for of motion for the carpool aren't too bad. I could write them out here, but I won't. I'm going to write them out. I'm going to just arbitrarily set all the parameters equal to 1 so that I have less writing to do, but it's not going to affect any of the details, okay? And even, just because it makes things a little easier, I'm even going to set gravity to 1. I normally don't do that, but it actually makes it makes a couple terms drop out that it's just less writing. Okay, so I apologize. I'm going to set even gravity to 1, okay? Okay, but if you do that, then you're rewarded with some nice and simple equations of motion. Yeah, there you go. Or you could do the same thing. I mean, you just scale the lengths and masses to 10 times what you originally planned, and you're all good. That's how I sleep at night, is thinking about it like that. Look at that. So much less writing. Okay? These are my equations of motion for the carpool. Remember, we now had, you remember the coordinates were the angle of the cart, of the pole, and the position of the cart, right? Okay, so I had two equations, two second order equations that describe it, and the F is the force on the cart, right? And then I have a 0 here. Okay, so let's see if we can do the same sort of thinking on this slightly more complicated system, okay? and try to think about regulating, let's say, the energy of this system. Now, it's actually the energy of this system is a coupled, complicated thing between the energy of the cart and the energy of the pole. And it turns out to actually be hard to, the picture of the Homoclinic Orbit disappears. It's not so clean. So what we're going to do is we're actually going to only reason about the energy of the pendulum still, where it has this nice homoclinic orbit. We're going to try to make sure that whatever the cart's doing, the pendulum lands on its homoclinic orbit and gets up to its upright. And then we'll try to do some extra little work at the end to make sure the cart does the right thing. Okay? Because actually the total energy of the pendulum, not that it's hard to write out algebraically, but it's hard to reason about a simple solution that gets to some unstable fixed point. Okay? So, but let's manipulate these equations a little bit more to get them into shape, right? So when you write it this way, you can sort of see that the dynamics of the actuated system, we have this second order differential equation here, which is my F affects the dynamics, this first equation. This one, you can really think of it as a constraint between theta double dot and x double dot. Right? I mean, you can always, every dynamic equation is a constraint, but let's think about this as having one equation that we can control actively, and then a constraint that relates the motion of the pendulum with the motion of the cart. Right? And then why is it useful to think about that? If I want to just think about the motion of, let's say, the cart, I can do that by solving away the second equation. Okay, so let's just think about, so if I, let's write down the theta double dot here is going to be x double dot c minus, it's a minus x double dot. Wow, that's a big C, and I wrote it like a little c, and I almost carried that down like a subscript. Let's fix that right away. That's a C as in cosine, not C as in some other thing, okay? Okay, so if I write this second constraint like this, you can think of it as a relationship between x double dot and theta double dot. If I insert that relationship back in that first equation, then what I end up with is 2x double dot plus, with this thing inserted, cosine is I can predict what the motion of the cart is going to be. It's a function of the force that you're putting in and the state of the whole system, including the angle and velocity of the pendulum, okay? But I can solve directly for x double dot. Okay? Did I miss a C? C is cosine theta. Yeah, C is shorthand for cosine theta. S is always shorthand for sine theta.
So S sub C is sine.
There's no sub C. I wrote it, and I actually tricked myself into thinking it was a sub C for some weird reason, and that's a big C. That's just that's x double dot cosine theta.
So is the one that's the dot?
Yep, same thing. That's a big C. That's just theta double dot cosine theta. Thank you for asking. I want that to be very clear. Yeah. It's just a shorthand to make myself write less. And I hope to make the ideas clearer, not get lost in the algebra. But the big idea here is not the where the C appears, but it's the fact that I can use that constraint equation here to write down the dynamics, the acceleration of the cart, purely as a function of the force coming in the current state of the system, right? So if I want to control x double dot directly, I could do that, right? Let's say I have x double dot desired. I could set my force, maybe I should simplify that once before we write it out. So what is it going to be? 2 minus c squared. Right? And then minus SC minus theta dot squared equals F. right? So if I choose, I can regulate exactly, I can use that force to regulate exactly my acceleration of my cart. If I have a desired acceleration of the cart, I could choose my controller to be 2 minus c squared x double dot desired, right? Minus sc minus theta dot squared. Right? That's something I can do as long as I have running estimates, running measurements of the angle and velocity of the cart. And I have a desired x acceleration. Okay. And if I put that back in, what I'll see is that x double dot equals x double dot desired. Right? This thing, I can make that claim because 2 minus c squared is never 0, right? Because cosine squared is always going to be less than 1. So I can cancel those out on both sides and say that x double dot is actually going to behave like x double dot desired. Yeah. Now, what does this smell like? This controller. Feedback linearization, right? But I actually didn't, and it is, okay? But it's not, I haven't feedback linearized the entire dynamics, right? I just feedback linearized one of the variables, right? So this is an example of something called partial feedback linearization. PFL is the acronym of choice, PFL, okay? And it's still bad. You should, I mean, whatever, you could still do sort of, you're still canceling the dynamics, okay? But it's going to be instructive here to see how this works, how this plays out. So first of all, is this surprising that we can do this? It's really not surprising at all that I can take the force on my cart, right? If I have a force on my cart and I want the cart to move through some trajectory or something like that, and I've got this annoying pendulum flapping around, okay? But I have a model of the pendulum. That what I'm doing here is I'm calculating the expected contribution of force, the coupling terms of the force of the pendulum, and I'm applying an extra force to cancel those out, and then I'm just making my cart do what I want on top. That's really not surprising that I can do that I can regulate it, and that's exactly what's happening. That's by solving this away, I'm just thinking about the contribution of that annoying pendulum hanging off the bottom to the cart, and I'm overriding it, and I can just drive my cart around. Okay? So that's partial feedback linearization. That's a specific idea of partial feedback linearization called co-located partial feedback linearization. Co-located. Because this is an example of partial feedback linearization where my actuator is on the same variable that I've linearized. Right? So I'm just taking all the annoying contributions from the rest of the system and I'm canceling them out, but I'm not, I've got a motor right there, so it's not surprising if my motor's big enough that I could cancel out all the coupling terms and just do it. Okay, what's more surprising is that you can often do non-collocated partial feedback linearization. So it turns out I could have also feedback linearized the dynamics of the pendulum, even though my actuator is on the cart. Okay? And the thing you can't do with an underactuated system is feedback linearize the entire system. But I can feedback linearize part of the system. Okay? So let's just see how that would go. Algebraically, you can sort of guess. If I have the same dynamics to begin with, my 2x double dot plus theta double dot c, right? So now I'm going to try to do the non-collocated feedback linearization. Okay, and I'll do it by just solving first for x double dot, and I want to solve this thing. I want to have this thing just in terms of theta double dot. Okay, so let me write down that x double dot is negative 1 over c theta double dot plus s. Okay, and then I'll stick that back in the first equation to get the whole thing in terms of theta double dot. So I'll get negative 2 over c Okay, and again, I can, if I choose, I could simplify this a little bit, but right? So now I can choose my dynamics to regulate the dynamics of the cart by just doing the partial feedback linearization. And that works most of the time, but it's not quite as good as before, right? Because that feedback linearization, something goes wrong here when I'm multiplied by infinity. It's not as good, yeah. Okay, but that's kind of cool. So I can actually use my actuator on my cart to completely make the pendulum do whatever I want. If I wanted to act like an upright pendulum, I could do that, right? If I wanted to do something and make it look like a damn pendulum, I could do that. What is this c equals 0 case where it doesn't work? What does that physically correspond to? Yeah, right? So the c equals 0 is when my pole is like this or on the other side, right? And in that case, there's nothing I can do with my cart to command the acceleration of the pendulum instantaneously. So what I've got to hope is that I don't stay there too long, right? And then as soon as I get back here, I should be okay again, right? Luckily, that's a sort of a very infrequent event, right? Okay, but that's pretty cool. So I could, if I used a lot of power, potentially, I could shove my cart around, and I could make it actually just have the dynamics of the upward, apart from that singularity. All right, and that's the big idea of sort of non-collocated partial feedback linearization. Okay. All right, so now we have a recipe for doing energy shaping of the pendulum with our controller even being at the cart, right? The first recipe could be, you know, right? The first idea would be let's just do non-collocated partial feedback linearization and just choose this. Just take the energy of the pendulum only and do the same controller I did before, right? And use the non-collocated PFL. And that works. Mathematically, it works. The problem is it's got that singularity, and so that actually means there's going to be times where I'm going to try to push infinitely hard on my cart, and that might not be something you want to do with your actuators. And here's where you get to think like a nonlinear dynamics, nonlinear control guy again. There's a nice sort of manipulation of the algebra that works much better than this. Gives you a much better controller that'll be more robust to the parameters, doesn't involve infinite force, and it's going to use all the same tricks. It turns out to use co-located PFL, which is nicer, right? It doesn't have any of the singularities. I'm just going to regulate the energy of the cart. And that gives me, if you remember, that gives me now my x double dot desired is followed exactly. But it also gives me some dynamics of my pendulum are implied by that constraint equation. They were this. Okay, so if I've made the cart dynamics like this, then the pendulum dynamics had to be that from that constraint equation. And so if I write the energy of the pendulum in my nice everything's 1, it just becomes theta dot squared minus MGL cosine theta, which is that. So if my error dynamics in my pendulum then just becomes, what's theta dot times theta double dot plus theta dot sine theta. If I insert this in, we're just understanding how the energy of the pendulum is changing given my commanded x acceleration, right? I get it turns out to be algebraically simple again. It's just negative x double dot theta dot cos theta. Okay? Which means, you know, by virtue of that, if I choose my controller, right? If I choose x double dot desired to be, now I've already got the negative over here, so I'm going to put in, sorry. Cos theta on top of what I had before. Then I get the same thing I had before, where the energy of my pendulum is going to go to the homoclinic orbit, is going to find its way to the upright, okay? By virtue of something that I did to regulate the position of the cart. And this time, this command, this transformation that made x double dot work, the co-located PFL is singularity free, and this is a nice gentle function, nonlinear function too. Okay, and that's going to work very well in practice, right? And specifically, the claim here is that E is going to go to E desired, just for the pendulum, so long as, you know, if somehow C does not equal 0 and theta dot does not equal 0 sort of infinitely often. Right? As long as I'm actually applying controls, I mean, this controller says do nothing if cosine theta equals 0. It says do nothing if theta dot equals 0, right? As long as I don't do nothing for all time, then I'll eventually find my way to the top. Right. Another way to write that is that the way that Mark Spong, this is Mark Spong's controller. He's got a nice paper. It's referenced in the notes from '96 about this. Okay. He says as long as the limit as time goes to infinity of theta dot squared cosine squared goes to infinity, then you'll stabilize the pendulum. Okay. All right. So that's really, it's just a simple example, but it's one that it captures the way to think about nonlinear control, a way to think about nonlinear control. And actually, a lot of the key results in nonlinear control have that sort of flavor. So, for instance, Jean-Jacques Slotin, who's in mechanical engineering, has a hugely powerful result about adaptive control for nonlinear manipulators converging into parameters and converging so that if you have a trajectory, even if you have unknown parameters of your robot arm, for instance, and you have a desired trajectory, you can say that I can adapt the parameters, my estimate of the parameters and the controller at the same time and guarantee that I'm going to get to my desired trajectory. Hugely powerful. It's only for fully actuated robots, but a hugely powerful result, okay, from adaptive control. And if you look at the proof, it's going to feel just like this. It's going to feel like I chose a controller of the form so that when I write down the error dynamics between the desired trajectory and the actual trajectory, I get something that is obviously positive times my error, and it goes to 0, right? It would take a lot more symbols to show you that, but a lot more notation, but the idea is really exactly the same. He had to be clever. He had to be extremely clever to come up with that controller. Mark Spong had to be clever to come up with a controller that not only you could prove goes to 0, but also doesn't go, is a nice controller to implement, has robustness, and works well in practice, right? But with that sort of moment of brilliance, you get these controllers that look like this that you can prove, okay? Now the actual controller you'd want to run on the pendulum, this thing stabilizes the pendulum, but not the cart, right? So we've promised that this thing's going to go up, but it could be that our pendulum just goes off, or our cart goes off to the side and just walks away, right? So in practice, you might do a little bit more, right? You might actually, in fact, one of the other advantages of using that partial feedback linearization on x double dot, in practice, what we can just say is x double dot desired is now k cosine theta, theta dot e tilde pendulum. That's what we had on the last slide. And I can add in an extra term to stabilize, a few extra terms to stabilize the position of the cart. Okay. And it's harder to prove that this thing converges, but for suitable choices of these parameters, you can prove it, and people have proven that. Okay. And that works too. I'll just show you it working. Now, you're gonna, as you can imagine, there's an equivalent story for the Acrobat, but we're gonna let you do that for your problem set. Okay. So I'm showing you the Carpool, but we'll let you do the. So let's look at the. Right, so I write down the pendulum energy here. I implement some saturations, okay, and then I write down this very simple controller, which is K1 times X, K2 times X dot, plus saturation times this thing we wrote down. Okay. I make my plant, I make my energy shaping controller, I feedback combine them, and I simulate it. And in the middle of making that controller, it's doing a sums of squares thing. It's doing an optimization to find the region of attraction, and somehow that got slower on this computer. I don't know why it's so slow today, but we'll make it fast before we get it to you. Anybody have any questions while it's computing the region of attraction? Yeah. Sure. And now we're going to miss the simulation, but yeah. I don't want to miss it. Wow. Something broke. Maybe the default degrees got set. We'll make that it should be like a heartbeat, right? Maybe we should call most second sensitivity too. All right, so there's another, I'll let that come up, but here we go. Yeah. All right, so that swings up and balances. It flips to the LQR controller. It does all the right things. Okay, so there's another thing you should realize is that the, and you'll make that work for the Acrobot in your problem set, okay? It's really just a good, healthy exercise. I almost feel like I should let that run a lot because we waited for it, but let's not. Okay, as time expires here, so it turns out the notion of partial feedback linearization is very general, right? So we did it in 2 specific cases. You can do it in general for the manipulator equations, right? So if I write down in general, I have my manipulator equations that look like this. Let me even simplify it. I'll lump C and G together. If I write this down, if I separate out Q into the sort of the actuated degrees of freedom and the unactuated degrees of freedom, these will be vectors, okay? Let's say, I'll do this as the actuated and this is the unactuated. Then I can write down this in a block matrix form. Okay, and I can write down a general form for partial feedback linearization that involves the inertial matrices, okay? And I can write it down basically for any manipulator. And the story is sort of what you'd expect. I can control Q double dot actuated always. I can control Q U double dot to the extent, now you have to understand the coupling between these equations, but coupling between those variables goes through these off-diagonal matrices, okay? It's the inertial matrix that couples the 2 equations, okay? So if you write down the full form of this, what you'll see is that if this thing is invertible, then I can control Q double dot U, and if it's not, then I can't, okay? And in general, I can pick some subset of the equations, right? So in general, if I say that y is some f of q, okay? If I have some function of my output that I'd like to command, I can set y double dot to be some y double dot desired if I have strong inertial coupling, it's called. Between my desired outputs and my control inputs, okay? And the strong inertial coupling is actually a very simple rank condition on a matrix, which is a function of h1, h2, and the gradients of f, okay? And that's in the notes, and I would have done it here if I'd had time, okay? But it turns out this notion of partial feedback linearization is very general for the manipulator equations. In general, if you have n motors, or m motors, let's say, I normally use m for the motors, then I can roughly control m quantities of my system with partial feedback linearization. As long as it's, so the times it's not going to work is that, let's say I have a motor attached to this desk, and I want to command something way over there, and they're just not attached at all. That's not going to work, right? And so the way that fails is that there's no inertial coupling between those 2, right? But if I have something where if I shake this, it moves over there, then I can make it work, potentially with a lot of power. Okay, excellent. I'll see you next time.